Pluto's perilous path. Could a collision with Neptune be looming? Pluto, the enigmatic dwarf planet dwelling on the outer edge of our solar system, is once again sparking curiosity and concern among astronomers. Recent findings suggest a potential for a close encounter, perhaps even a collision, with Neptune. This possibility has raised alarm among experts and space enthusiasts alike. Renowned figures such as Neil deGrasse Tyson and Miyoku have weighed in, warning of the significant implications a cosmic collision could have, not just for the planet involved, but potentially for Earth as well. But how did Pluto end up on a trajectory that may intersect with its distant neighbor? And what could such an extraordinary impact mean for the delicate balance of our solar system, a planetary outlier? Once classified as the 9th planet in our solar system, Pluto was redefined as a dwarf planet due to its unusual orbit. Yet this change in status has done little to diminish its intrigue. With an orbit that takes 248 Earth years to complete, Pluto still hasn't made a full trip around the Sun since its discovery in 1930. Its orbit is both steeply inclined, tilted 17 degrees from the ecliptic plane, and highly elliptical, setting it apart from the relatively circular orbits of the major planets. One of the most puzzling features is that Pluto's path actually intersects Neptune's orbit for roughly 20 years of its orbit. Pluto comes closer to the Sun than Neptune, a counterintuitive situation that seems to invite disaster. Why a collision hasn't happened yet? Despite the apparent danger, Pluto and Neptune have never collided. This puzzling stability can be explained through gravitational mechanics and resonance. The orbits of Pluto and Neptune are locked in a 3:2 resonance. Pluto completes 2 orbits for every 3 Neptune makes. This gravitational synchrony ensures they never occupy the same space at the same time. Key to this protection is a phenomenon called libration. Even when Pluto crosses Neptune's orbital path, it is always at least 90 degrees away from Neptune in angular separation. Additionally, Pluto's orbit takes it well above or below Neptune's orbital plane, offering another safeguard against impact. The chaotic beauty of Pluto's orbit. Despite this resonance-induced stability, Pluto's orbit remains a subject of intense study due to its inherent chaotic behavior. In the late 1980s, simulations showed that even slight differences in Pluto's initial position or speed could cause major changes in its orbit over millions of years. This sensitivity to initial conditions, a core feature of chaotic systems, makes long-term predictions difficult. Terms like IML, indirect mean motion libration, and Kozai oscillations help describe the gravitational dynamics, keeping Pluto's path relatively stable. These complex interactions create a balance between order and chaos, allowing Pluto to maintain its unique orbit over billions of years, despite its unpredictability over shorter timescales. The role of the giant planets. Massive planets like Jupiter and Saturn also contribute to Pluto's orbital stability. Jupiter's immense gravity exerts a strong influence across the solar system, while Saturn's more subtle pull helps shape long-term orbital dynamics. Together with Neptune, these giants create a gravitational framework that keeps Pluto in check. Without these stabilizing forces, our solar system could be far more chaotic, with frequent collisions or planetary ejections disrupting celestial order. These interactions are vital to understanding why orbits that seem unstable on the surface often persist across cosmic timescales. Astrophysical warnings and the public fascination. Despite these stabilizing factors, some experts remain uneasy. Prominent astrophysicists like Neil deGrasse Tyson continue to caution that our knowledge of celestial mechanics, though advanced, is not complete. Tyson, known for demoting Pluto to dwarf planet status, views this not as a slight, but as an evolution in our understanding of the solar system. He emphasizes that Pluto's quirky orbit and potential for future instability underscore the need for continued observation. For Tyson, events like this aren't just scientific curiosities. They're opportunities to engage the public's imagination and remind us of the vast, dynamic nature of space. Conclusion: a universe in motion. Pluto's unusual behavior offers a window into the dynamic interplay of gravity, motion, and time. Though a collision with Neptune remains highly unlikely due to current orbital mechanics, the mere possibility underscores the fragile balance that governs planetary systems. Pluto serves as a case study in how chaos and order coexist in the cosmos, and why we must remain ever curious about the mysteries of our universe. As we refine our simulations and deepen our understanding, we edge closer to answering some of space's most fascinating questions. And in doing so, we recognize just how much remains beyond our grasp. Potential dangers of Pluto's unusual orbit and the three-body problem. After extensive analysis of Pluto's orbit, experts have raised alarms about the potential risks it poses, particularly in the context of the three-body problem, a complex gravitational interaction involving Pluto, Neptune, and the Sun. Some scientists suggest that a long-overdue collision between Pluto and Neptune could one day occur. Astrophysicist Neil deGrasse Tyson has highlighted how such an impact might disrupt the delicate gravitational balance of our solar system, with potential ripple effects extending far beyond the outer planets, even reaching Earth. A collision between Pluto and Neptune would be an exceptionally rare and catastrophic event, given Pluto's relatively small size and icy composition. Such an impact could cause it to completely disintegrate, releasing immense amount of energy. The resulting debris might scatter throughout the solar system, potentially threatening other planets and their moons. For Neptune, the consequences could be equally dramatic, possibly altering its atmosphere or orbital path depending on the specifics of collision. Dr. Michio Kaku, a renowned theoretical physicist known for his work in string theory and science communication, offers a deeper theoretical perspective. He views Pluto's orbit not just as a curiosity, but as a key to unlocking insights into the future of space exploration. According to Kaku, understanding the gravitational interplay of distant bodies like Pluto is critical for planning future deep space missions and navigating the outer solar system. These lessons, he argues, can also inform our approach to exploring exoplanets and other celestial bodies. Kaku emphasizes a strong link between celestial mechanics and fundamental physics. The orbital dance between Pluto and Neptune isn't just a local phenomenon. It reflects the underlying laws of nature. His work in string theory, which aims to unify all fundamental forces by modeling particles as one-dimensional strings, could be directly informed by high-energy cosmic events like a Pluto-Neptune collision. Such an impact could generate extreme conditions of gravity and energy, offering a rare chance to test predictions of string theory in a real-world setting. For example, gravitational waves emitted during the collision could provide data critical to understanding how space-time behaves under intense stress. Though Earth is far enough from the outer solar system to avoid direct consequences, the scientific value of such an event would be enormous, potentially advancing our understanding of the universe at its most fundamental level. Pluto's orbit, shaped heavily by Neptune's gravity, serves as a remarkable example of the tension between order and chaos in space. It illustrates how celestial mechanics, governed by complex gravitational forces, can create both long-term stability and sudden instability. The three-body problem remains one of the key challenges in physics, offering clues to the hidden dynamics of planetary systems. While planetary collisions are exceedingly rare, they are not impossible, and systems like TRAPPIST-1, with its 7 Earth-sized planets in tight orbits, remind us that the universe still holds many surprises. Gravitational forces can create rhythmic patterns known as orbital resonances, which, over time, may destabilize planetary orbits and increase the risk of collisions. In densely packed systems like TRAPPIST-1, such interactions are carefully studied, though no collisions are currently occurring. Scientists closely monitor these systems to better understand how nearby planets influence each other's movements, especially when they orbit in close proximity. Adding to this cosmic complexity are rogue planets, maverick worlds that drift through space without orbiting any star. These planets were likely once part of a star system, but were ejected due to gravitational disruptions or major cosmic events, such as the close pass of another star or dynamic instability within their own system. As these wanderers travel across the galaxy, there's a remote possibility they could pass near or even enter another planetary system. In such rare scenarios, a collision could occur. However, the vastness of space, combined with the low density of planets in open interstellar regions, makes such direct impacts extremely unlikely. Moreover, rogue planets are relatively rare compared to the number of stars and orbiting planets, further reducing the chances of such encounters.